Modern commercial agriculture has a single massive point of failure. It requires a continuous connection to the macro internet to function. Heavy machinery manufacturers use proprietary cloud services to control their equipment. If a tractor loses its cellular signal in the middle of a planting field, the internal software locks up, turning a $500,000 machine into a multi-ton paperweight. Traditional ag data flows from tractors to cell towers, then corporate servers. Any interruption halts operation. Sovereign Harvest replaces this with an enclosed loop between tractors, sensors, and a barn server, scaling a hybrid mesh across thousands of acres to connect everything simultaneously. Because the network is physically air-gapped from the macro internet, not a single byte of machinery telemetry, genetic logging, or yield data ever leaves the physical boundaries of the farm. We are going to map the physical deployment of this system from the ground up to demonstrate exactly how a large-scale autonomous farm operates entirely offline. While legal debates over repair rights continue, this architecture addresses the problem at the structural level. It replaces proprietary manufacturer software locks with a completely sovereign, air-gapped hardware stack. This 3D topographical map shows a commercial farm's blank slate. We must account for massive acreage, hills, and dense infrastructure. The foundation is the core compute layer, two physical server clusters placed in separate outbuildings, typically the main office and a secondary barn. These are high-capacity Sentry Pro clusters, providing a total of 6 individual server nodes. Deploying them across separate buildings creates an active-active redundancy design. If a fire or power surge destroys the primary office cluster, the secondary barn cluster instantly takes over the network load without interruption. These clusters host the DevOps Sovereign Operating System, which uses an administrative AI agent called DeepAdmin to ingest and manage the farm's operational data. Their first task is to mint the farm's unique root CA. A root certificate authority is the top-level cryptographic key that validates device identities and secures communication channels on a specific network. By minting the root CA locally on these servers, the farm's sensors and tractors can instantly verify each other's identity and establish secure connections without needing to check an external internet server. True data ownership relies strictly on this physical compute layer. Housing the servers on site isolates the digital nervous system, making external cyber attacks virtually impossible. With the core compute established, the next engineering challenge is projecting that network across thousands of acres of dense crops and steel infrastructure. We now at 5 high-gain LoRaWAN towers on silos for deep field penetration. LoRaWAN transmits small data packets over long distances with minimal power, projecting overlapping coverage cones across fields. For heavy traffic, 50 Wi-Fi 6E mesh points create a dense, high-speed bubble around processing facilities. This dual-frequency canopy provides the infrastructure for an IoT grid powered by 500 industrial Foreman micronodes. These solar-powered bridges are seeded into the planting fields, instantly drawing connection lines back to the central LoRaWAN towers. These micronodes monitor the physical environment, continuously transmitting data on soil moisture, weather conditions, and NPK levels. NPK stands for nitrogen, phosphorus, and potassium, the 3 primary macronutrients required for crop health. The micronodes also physically interface with existing third-party sensors out in the dirt, pulling their localized readings directly into the farm's sovereign ecosystem. This generates millions of specific, localized data points that stream into the core clusters in real time. Splitting the radio frequency topology between low-bandwidth towers and high-bandwidth nodes results in a resilient, self-hosted internet covering every square inch of the operation. But static towers have physical limitations, creating topographical dead zones. As the map rotates to this valley, we see a cluster of field sensors flashing red. Environmental factors like rolling hills or dense tree lines physically block radio signals, isolating these sensors from the main tower's broadcast cone. A network relying strictly on static infrastructure will always suffer from coverage gaps in highly variable agricultural terrain. Nomad fleet kits enable a tractor as a relay protocol. When a tractor drives into the blocked valley, isolated sensors connect to its receiver, caching stranded data internally. Exiting the valley, the tractor bursts that cache data back to the core servers. This store-and-forward caching process actively patches structural radio interference without the need to build and wire additional towers in remote locations. This transforms the moving multi-ton machinery from a passive endpoint into an active, dynamic extension of the network itself. The machinery moving through these fields represents massive kinetic power, and integrating that power into a localized network requires specialized hardware. Technicians plug the Nomad Fleet Kit directly into the machinery's ISOBus or J1939 CAN bus diagnostic ports. A CAN bus is a standard that allows microcontrollers and devices to communicate with each other's applications without a host computer. Bridging the network into this specific port grants the edge node complete mechanical and steering control over the vehicle. This level of control introduces a critical security risk: machinery hijacking. If a bad actor intercepts the local mesh, they could attempt to send spoofed steering commands to crash a harvester. To prevent hijacking, the industrial foreman node uses strict X509 signature verification. In this flowchart, a data packet arrives and is scanned. Unsigned packets are instantly rejected and flagged. Conversely, valid cryptographically signed packets pass through, translating directly into RTK GPS auto steering commands. By enforcing decentralized kinetic security at the machine level, heavy equipment can operate autonomously and safely without ever pinging an external cloud server for permission. With the hardware, network, and security layers established, the Sovereign Harvest architecture operates as a single, holistic entity. The autonomous harvest loop begins when the remote field sensors detect optimal crop maturity and ideal soil moisture levels, reporting this telemetry back to the core server. The Deep Admin AI ingests this data, calculates the most efficient path based on weather and field topography, and automatically schedules the harvest route. Out in the field, the combine harvester receives the schedule and executes the GPS-guided route, driven entirely by the onboard industrial foreman unit. As the combine reaches full capacity, it pings an autonomous grain cart over the local mesh network. The cart dynamically routes itself through the field to pull alongside the moving combine and accept the offloaded grain. This entire logistical operation, coordinating thousands of pounds of moving steel and harvested crops, executes with zero human intervention and zero reliance on the macro internet. Simultaneously, on the other side of the property, a rancher inside a metal barn examines a calf, dictating hands-free medical notes using a localized Whisper AI headset. Those dictated notes are instantly transcribed and logged into an air-gapped PostgreSQL database. PostgreSQL is a highly stable, open-source relational database management system. Because it runs strictly locally, these genetic records remain completely invisible to external tech vendors or commodity traders. By taking physical ownership of the compute hardware, the radio frequency canopy, and the cryptographic layers, commercial farms permanently reclaim their operational sovereignty. Their yield data, their heavy machinery, and their livelihoods remain entirely their own.